Welcome to For the Love of Physics podcast. We are Mr. Jager's assistant. A big hello to all the students at Ishik Boys High School, especially Mr. Jager's class. Today, we're doing a deep dive into something pretty fundamental, how light interacts with our atmosphere. We're going to unpack two ideas you might see in your physics work, scattering and how that leads to polarized light. We've got some great textbook material here, and our mission, really, is to pull out the key stuff, make it clear, and sort of see how it shows up in the real world.
Yeah, and it's fascinating because, this stuff explains things we see all the time, but maybe don't really think about, like the actual light you see when you just look up at the sky. It's quite subtle.
Right, this hidden dance, as you put it. Okay, let's get into it. Scattering. When we say light scatters, what's, the picture we should have in our heads? What's happening there?
Okay, so scattering, the textbook definition is basically the absorption of light by atmospheric particles, and then it gets radiated again. So it's not just light bouncing off like a ball off a wall.
Ah, okay. Absorption first.
Exactly. It's absorbed, taken in by the particle, held for a tiny moment, and then re-emitted, sent back out. But importantly, it's sent out in, well, pretty much all directions.
So it gets taken in and then sort of sprays back out again.
Kind of, yeah. And this happens specifically when the light hits particles, could be air molecules, tiny dust bits that are roughly the same size as the light's wavelength. That's the key condition.
Right. So absorbed, then re-radiated in all directions, not just bouncing.
Got it. Okay, so how does that whole process, how does scattering connect to this thing called polarization?
It flows directly from it. As we said, light scatters in all directions. But here's the really interesting bit. The light that gets scattered in any one specific direction, it actually becomes partially polarized.
Fully polarized, okay.
But there's a special case. The light that gets scattered in a direction that's exactly perpendicular-like at a 90-degree angle to the way the original light beam was coming in. That scattered light becomes completely polarized. Completely polarized. What does that mean exactly? Like, what does the light look like, or how does it behave differently?
It means its vibrations are lined up. You know how light is an electromagnetic wave? It has these vibrations. Normally, in unpolarized light, like sunlight, the vibrations are happening in all directions, perpendicular to the way the light is traveling.
Okay, like shaking a rope randomly up, down, side to side, all at once?
Exactly like that. But when it's completely polarized, it's like you're only shaking the rope in one direction, say just up and down. The vibrations are now all confined to a single plane, and that plane is perpendicular to the direction the light beam itself is moving.
Okay, I think I can picture that. Only vibrating, say, vertically, while still moving forward horizontally. So, why does scattering do that? Why does it force the vibrations into one plane?
Well, this gets into the mechanism, the sort of nuts and bolts. It involves the electrons in those atmospheric particles. When the unpolarized light wave hits a particle.
Like a nitrogen or oxygen molecule in the air.
Precisely. The electric field, part of that light wave, makes the electrons inside the particle start to vibrate, to oscillate. They get jiggled by the light, essentially.
Okay, tiny vibrating electrons. And those vibrations are what re-radiate the light?
Yes, exactly. Those vibrating electrons act like tiny antennas, sending out new light waves. That's the scattered light. But here's the crucial part for polarization. An electron vibrating in a certain direction cannot radiate light effectively along that same line of vibration.
Okay, say that again. It can't radiate along its vibration direction.
Right, so imagine sunlight coming down. Its electric field makes electrons in an air molecule vibrate both horizontally, parallel to the Earth, and vertically. Now, if you're standing on the ground looking straight up, and the sun is, say, behind you.
Okay, sun at my back, looking up.
The light coming down towards you from that patch of sky was scattered at roughly 90 degrees from the original sunlight pass. Now think about those vibrating electrons up there. The ones vibrating vertically, up and down, they can radiate light out sideways toward you. But the ones vibrating horizontally towards and away from you along your line of sight, they can't effectively radiate light towards you along that same direction.
So the light I see looking up is mostly coming from the electrons that were vibrating vertically.
Well, in that specific setup, it's the horizontal vibrations relative to the ground that produce the polarized light you see traveling parallel to the Earth towards your eye. The key is that you're only effectively seeing the radiation from vibrations that are perpendicular to your line of sight. The atmosphere acts like a filter based on the geometry.
Wow, okay. That makes sense. The geometry of the scattering and the physics of electron radiation sort of filter the light for you? So this isn't just theoretical then, we can actually observe this.
Absolutely. This is something you can see any clear day. The source material points it out directly. An observer with his or her back to the sun will see polarized light when looking up toward the sky.
So literally, sun behind me looks straight up.
Mhm.
That skylight is polarized.
A significant portion of it, yes. It's a direct result of this scattering by the air molecules.
Yeah.
And you can even test it. If you have polarized sunglasses,
Oh, yeah.
try it. Look at the blue sky, maybe 90 degrees away from the sun, and slowly tilt your head or rotate the glasses. You should see the sky get noticeably darker and then lighter again.
Because the glasses are blocking the polarized light when they're oriented the right way.
Exactly. The sunglasses only let light vibrating in one specific direction pass through. So as you rotate them relative to the polarized skylight, you change how much of that light gets through. It's pretty cool direct evidence of this physics happening way up there.
That is cool. It really brings it home. It's not just equations, it's the actual sky. Okay, so let's quickly recap. We talked about scattering, how it's light getting absorbed by tiny particles and then sent back out, re-radiated. And we saw how the scattering process naturally leads to polarization, especially when the light scatters at a right angle to its original path. And the why involves electrons in the air particles vibrating and how those vibrations create the new, often polarized light waves. Which all leads to the fact that the blue sky above us, especially in certain directions relative to the sun, is actually polarized.
Precisely. A beautiful interplay of light and matter happening constantly. So thinking about all that, here's a little reflection for you, the listener, based on what we discussed. An observer looks at the sky with his back to the sun. How would you explain, in your own words, why they observe polarized light? Think about the path of the sunlight, the scattering, and those electron vibrations.
Give that some thought, and remember, stay in contact with your physics teachers, stay creative.